Recording. Okay, here we go. So this is Chem 129. We're doing some office hours right now. There's just a few 129 folks in here, so other classes, sorry. But we're looking at, which question is this?
It's number 8 from MQ 1.2.
1.2, number 8. And it's a fairly long question. It talks about the solubility. It's doing a comparative solubility between
silver and magnesium.
With phosphate. And when we look at the KSP values for silver phosphate and magnesium phosphate, we come to a certain conclusion. Ag3, PO4, KSP is equal to
2.6 times 10 to the negative 18.
And for Mg3, PO4, 2, KSP is equal to
5.2 times 10 to the negative 24.
Right, and this is where we get into one of our traps. If we just compare KSP values, we might not pick the correct thing for precipitating first. And that's a weird situation to run into, because most of the examples I've done in class, KSP value, can just look at that. And I'm thinking this might be the issue, so I've got to do some math to check it, but I'm going to explain why this could be an issue. And the part that I think is important is doing the homework versus using the homework. So doing the homework is going through, getting your green bars and being like, yes, I got it. And you do each problem, and each problem is its own problem, right? And you do that problem, you're on to the next problem, that problem, on to the next one. The using the homework, the homework's not worth much, right? 5% of your grade over like 20 assignments over the quarter. Most of it's just participation with the homework. Like, the homework is not worth a lot. It's easy to get those points if you just want those points. So it's not supposed to be busy work. The question becomes, the using the homework aspect is, after you've got it, when you look back, can you recognize a pattern in the way that the problems relate to each other, in the way that all of these individual ideas kind of form this larger scale of what's happening in chemistry? And there was this thing that happened with the KSP value, where the solubilities and the KSPs, or the molar solubilities and the KSPs, are not always exactly relatable to each other. And that's because if we do the solubility table for silver phosphate, Ag3PO4 solid, goes to 3Ag plus PO4 3 minus 0 0 plus 3x plus x 3x x. We're going to end up with KSP is equal to 3x cubed times x. I know you can all follow this along, but I just want to set up the magnesium phosphate at the same time. Mg3PO4 2 goes to, getting ahead of myself, 3 Mg2 plus 2 PO4 3 minus, that's going to be 0 0 plus 3x plus 2x 3x 2x. We're going to end up with KSP is equal to 3x cubed times 2x squared. So notice, for that first number, 10 to the minus 18, I'm going to take the fourth root. And for that second number, 5.2 times 10 to the minus 24, I'm going to take the fifth root. Because there's different numbers of ions that it's disassociating into, the math is slightly different between the two. Which means KSP value is not always does not always exactly tell us which one is going to precipitate first. It's really the molar solubility we have to look at. Now, I'm not saying that this is where your problem is going wrong right now, but that's something important for us to consider. The other possibility is the thing you were asking about is, is the X's small approximation failing anywhere in this problem? How do we tell if the X's small approximation is going to fail? Now, generally, so let me ask another piece of information about this problem. What were the concentration in silver and magnesium that we were trying to disassociate here? Or sorry, trying to separate.
You mean the starting concentration?
Starting concentrations.
The silver was, the silver was 0.43 molar, and the magnesium was 0.32 molar.
Okay. So from those two molarities, right away, I think the X's small approximation is going to work great everywhere. Why?
Because it's
KSP values are on the order of -18, -24. Concentrations on the order of -1. As long as I've got a factor of 10,000 difference, 5 orders of magnitude, I feel pretty safe using the X's small approximation. Now, that's not exactly true because when I'm taking fifth root, it needs to be like a factor, it needs to be more orders of magnitude. When I'm taking a fourth root, it needs to be more orders of magnitude. If I'm just taking the square root, 5 orders magnitude, 4 orders magnitude is probably plenty. If I'm taking a fifth root, it might not be as good.
okay.
So generally what we're going to do is we're going to use the X's. So we'll have some sense of, I'm going to, like you'll notice sometimes I'm like, ooh, I'm going to use the X's small approximation, I'm worried about it. Because my concentration and my KSP values are similar, or like, are too similar.
Yeah.
Like even if they're within a factor of 1,000 of each other, I think they're like too similar. Or if I know if they're within a factor of like 10,000, but I'm taking a fifth root, that also worries me. I'll still do it, and then I'll check if it was good at the end.
Okay.
So let's go ahead and do this problem. This is 1.2 number 8. You might have different concentrations because the numbers are somewhat randomized. But let's go ahead and do this one and see where it goes. First, let's calculate these and see if the molar solubilities throw the order out of whack. Because that might be what's happening. I'm not sure, but let's check. I'm going to do 2.6 times 10 to the minus 18 divided by 27 to the power of 0.333333. And please double check my work because I am definitely fallible. 9.87 times 10 to the minus 7. Pretty good molar solubility. I'm going to do the same thing here with this one. We actually probably have this one from our notes last week because we did this one in class together, but I'm just going to do it again right now. 5.2 times 10 to the minus 24 divided by 108 to the power of, what's 1/5? 0.2? Ooh, this does throw things off. Oh, no, it doesn't. Oh, no, it does. X is equal to 8.64 times 10 to the minus 6. The one with the smaller KSP has a bigger molar solubility. Weird. But that's because fifth root instead of fourth root. This also makes me worry. We haven't talked about this yet in class, but this also makes me worry. The fact that these two molar solubilities are really close to each other makes me think this is going to be a terrible separation. So we haven't talked about what makes a good separation versus a bad separation. But this is the weird thing that was happening to you where it was like, oh, you got everything backwards. Yeah. The mathematics still come out approximately the same. The math is the same. But the conceptualization is slightly different. Right? Because of the different number of ions, it actually turns out magnesium phosphate is going to precipitate first, which we would not guess from the KSP values.
I think you mean
sorry, precipitates later. It has a higher solubility. The silver phosphate is actually going to precipitate first. So when I go into making my map of consideration, right? So when I do these things, I'm going to leave this work here, but I'm going to erase the chemical reactions for a second. When I do my consideration of how does this separation problem work, I draw a little picture. where I have to identify, well, what's going to precipitate first, what's going to precipitate second. And in this situation, the thing with the lower solubility is going to precipitate first. So this is going to be the point where Ag plus is saturated. As my phosphate concentration is going up. Right? As my phosphate concentration is going up, I'm going to find it takes a lower concentration of phosphate to saturate the silver, right? That's a lower concentration of phosphate. And actually, this one, if I want my concentration of phosphate here, I actually need 2x to get my PO43 minus concentration here, which is going to be equal to 1.728 times 10 minus 5. So if I go to phosphate concentration, it's an even higher concentration of phosphate if I was just doing it in water. So I'm going to get my Mg2 plus concentration is saturated at a higher level. Now, this is not exactly how our math is going to work out. I can't just reuse these numbers over here because these are in water with no ions present. This has ions present. But this is how I'm thinking about it, right? It just, from looking at these solubility values, the silver is going to saturate at a lower concentration than magnesium, which we would not get if we just compare the KSPs. Kind of weird. Kind of weird. Does that make sense to you?
Yeah.
Okay, cool. At this point now we're just doing the same thing we did in class. I'm going to erase this bit because that math is actually not useful to us in solving this problem. Now we're just going to do 2 equilibrium tables. I'm not going to calculate the concentration to saturate the silver. Because wait, does the problem ask for that?
Yeah.
Oh, great. Okay, then we will do that one. After we do a couple of these like warm-up problems where we calculate all the different pieces, a lot of times it's just like, what's the point of maximum separation? So they stop asking, like, we don't really need to calculate this. It just cares about maximum separation, not the lower concentration. But since the problem specifically asks us to do this, we'll go ahead and do this. So I'm going to give myself a little bit more space. Put my saturateds here.
So would you recommend that we check the molar solubility only if they're really similar KSPs like that?
Well, there's 2 things that make it so we have to check the molar solubility. If they are disassociating into different numbers of ions, 4 ions, 5 ions, and the KSPs are getting close to each other, then we want to check. You'll notice on a lot of the examples in the textbook and the examples I do in class, and most of the examples on quizzes and exams, it's going to be comparing things with the same number of ions, so you don't have that extra worry. I always try to do at least one really complicated problem on the homework, just so you can see like the most difficult problem I could write. I don't want you to see the most difficult problem I could write on the exam. I want you to see it before then.
Okay.
So this is a pretty difficult one in terms of this separation, right? The one we did in class was all square roots, super easy. A couple on the homework are all square roots, super easy. Right? Everything's the same number of ions. This is the only one where it's like, not only is it different number of ions, but it's 5 ions in solution is kind of the most that I think we'll see this quarter. So like phosphate with a +2, like magnesium phosphate, or the copper phosphate we did in class today. Those are kind of like the hardest math we do. So let's go ahead, let's start with doing the silver calculation. At this point now, it's just doing the same thing. But we're going to double check some interesting math, and I wonder if you had this in your math and you didn't, like you did the work, but you didn't notice the usefulness in it. So let's go ahead and do this and see what happens. We're going to do this with silver, so we've got Ag3 PO4 solid, going to Ag plus 3 of those, aqueous, plus PO4 3 minus, aqueous. Not worrying about that. Here we've got 0.43, we've got 0, we've got plus 3x, we've got plus x, we've got 0.43 plus 3x, we've got x, and I'm just going to plug everything in. 2.6 times 10 to the minus 18 is equal to 0.43 cubed, approximate, times x. I'm going to solve for an x concentration. Notice I'm using the x is small value approximation here because I've got a 2.6 times 10 to the minus 18 KSP and 0.43 for my initial concentration. Can't really tell if this is good. If you remember my check for if the approximation is good or not, I need my x value to tell if the approximation is good or not. So I'll go ahead and do this calculation and see what my x value is. 2.6 times 10 to the minus 18 divided by 0.43 3.2 times 10 to the minus 17.
That's, yeah.
Cool. And now I'm just going to do it in my head. I'm going to do x divided by initial concentration, which is 0.43. So 3.2 times 10 to the minus 17. I'm not even going to say that number of zeros. Divided by 0.43. Yeah, that's gonna be way smaller than, that's going to be like something on the order of 10 to the minus 16. That's going to be really small. So that is my phosphate concentration. That's my phosphate concentration to hit this saturation point for silver. I did the same calculation for magnesium. Forgot my states of matter. Magnesium is at 0.32 concentration. Phosphate is what we're trying to figure out, so it's going to be 0, and we're going to add phosphate to get it up to the proper concentration, plus 3x plus 2x. So notice the math is already different, plus 3x versus plus 2x. 0.32 plus 3x and 2x. Then I'm going to go ahead and plug this in. I'm going to have 5.2 times 10 to the minus 24 is equal to 0.32 cubed. And let's get the approximate on there so I know I'm doing an approximation. And 2x squared. My x value in this situation is going to be a little different. 5.2 times 10 to the minus 24 divided by 0.32 to the power of 3. That divided by 4 is equal to that square root 6.29 times 10 to the minus 12. Oh yeah, and then multiply that by 2 to get it to phosphate concentration. Thank you, I almost forgot that. And then my PO4 minus, sorry, I'm scrunching it in the corner. Is that even on the camera? That's not even on the camera. There we go. Is 1.25 times 10 to the minus 11. Which phosphate concentration is bigger, the one to saturate silver or the one to saturate magnesium? Magnesium is the bigger concentration. That means silver is going to precipitate first. So even if we didn't do the KSP comparison correctly, we're like, oh, silver is going to be first. When we calculate the X value or the phosphate concentration for each, like if I had my magnesium and my silver flipped on my little picture, when I write my numbers in, my magnesium number is bigger than my silver number, and I'd be like, wait, something's wrong. The thing that's wrong is square root versus no square root, right? If you didn't take that square root, the magnesium phosphate would have precipitated first, but you wouldn't have been taking into account the energy of magnesium ions into solution correctly. So that's the other place we could have seen it. We calculate the two phosphate values, and we're like, whoa, magnesium precipitates first. And again, I don't need to do the check for my X is small approximation because this X is so tiny. I know it's fine, right? That's definitely 10 to the minus 12 is really tiny. So also notice, in doing this, both of these things really want to precipitate. The detail, the concentration to get this to selectively precipitate is going to be impractical for us to do in a laboratory setting, unless we have some really fancy industrial equipment. Because the concentration we need to hit in order to maximize separation is 1.25 times 10 to the minus 11 molarity. That's on the scale of picomolarity. That's like super, super small. It's really hard. Like things on the scale of nanomolarity are already like really difficult to do. Anything below micromolarity, and I'm like, well, are you kidding? So this would be, in terms of mathematics, in terms of doing a conceptual problem, yeah, we can do this. If I asked you to go do this in a laboratory, it'd be really hard. But we can do the conceptual work. And then we can, pay someone else to figure out how to do it in the lab. Okay. Or, patent it, market it, and, someone in the private sector can pay for our patent. However you want to go about the world. So, we're not done with the problem, though. We've got our point of maximum separation. I'm going to write these numbers down so I can erase stuff and get more space.
I just have a clarification.
Sure.
So by smaller, do you mean by these numbers right here, or by the very sig figs?
I mean by the whole number, right?
Okay.
1.25 times 10 to the minus 11
Okay.
is bigger than 3.2 times 10 to the minus 17.
Okay.
So I'm going to have here, where can I put this? I'll put it here. 1.25 times 10 to the minus 11. So this is going to be my phosphate concentration for that one versus my 3.2 times 10 to the minus 17.
1.25 times 10 to the negative 11 is the point of maximum
Separation. Yeah. So when I look at this, because that is the point. So that concentration is the point where if I hit that concentration, I have to put in more material to get the silver to react and everything. Mm-hmm. But if I hit that concentration level, that really, really small concentration level, I theoretically will have knocked all of my silver out of solution and none of my magnesium. Now, how could this be useful and why might somebody do this? Silver mines didn't do this with phosphate. They did it with something that had better separation. But if I precipitate all of my silver, I could now collect that silver and get rid of the magnesium. And now I've got essentially, it's silver phosphate, but I can do some secondary reactions. I can do some electrochemistry to get silver metal and I can make some money off that. Right? I can separate, if you've got this big slurry and you're like, oh, there's silver in this, but it's mixed up with magnesium. I can now knock the silver out, take that solid out, and have something that I can turn into silver metal. And silver mining actually used to be done with something similar using competitive solubilities, using sulfides and mercury. So never play in abandoned silver mines. If they're old, they used to actually spray mercury inside of them and arsenic to get the silver to go into solution by doing selective precipitation with the mercury. And then they would collect it, and then they would clean it out, and they'd end up with pure silver, but those mines are all super contaminated now. There was one in the mountains next to where I grew up, and a bunch of warning signs that didn't make sense to me as a kid. So I was like, I don't care, this is a cool mine. Yeah, super, super unhealthy situation. So I'm gonna erase this work for these first two parts, and we're gonna answer the last question, kind of most interesting one, which is how much separation have we actually done? All this careful work getting to this really absurd concentration. At this point, my silver concentration should be approximately 0. But what is it actually?
So for this one, I kind of just plugged in the point of maximum concentration or separation, 1.26 for the phosphate, and then set that equal to 27x cubed.
Perfect. Yeah, that's what we do. We go magnesium 2+. Nope. We do magnesium phosphate, 2, PO4, 3, solid. It's going to go to magnesium 2. Oh God, what am I doing? Silver. Jeez. Mondays, right? Silver, yeah?
Yeah.
Because we want to figure out, we have it approximately 0. We actually want to figure out what it is. We're going to have Ag3, PO4, going to Ag plus, 3 of them, plus PO4, 3 minus aqueous, solid. And our question is, my silver has theoretically completely precipitated. I theoretically have 0 silver left in solution if I have a concentration 1.25 times 10 to the minus 11 molarity here. But what is it actually, in this situation, what is it actually at equilibrium? Now, since I've got 0 silver, I know 0 silver ions in solution is not real, so I have to have a plus 3x there, a plus x there. I'm going to have 3x, and ooh, back to your original question of when is the x small approximation good, I'm nervous about this one. Look at my initial concentration value here. 1.25 times 10 to the minus 11 plus x. 1.25 times 10 to the minus 11 is a really small value. Now, KSP value is 2.6 times 10 to the minus 18. It's off by a factor like 7 orders of magnitude, so it's 10 million times different. But minus 11, I've got a cube root I'm going to have to do. I'm really worried my x small approximation is going to fail. Does the problem tell us to use it anyway?
Doesn't say anything about
Okay. I might have to add a note to that, but let's do this and let's see what happens. I think it's going to fail, but let's do it anyway and see. Because we can't check if it fails or not until we have our x value.
Okay.
So let's go ahead and do it. We're going to have 2.6 times 10 to the minus 18 is equal to 3x cubed times 1.25 times 10 to the minus 11. That's approximate. And we go ahead and solve this, and we see what x value we get. 2.6 times 10 to the minus 18 divided by 27 divided by 1.25 times 10 to the minus 11. That. Take the cube root. Oh, we're in trouble. X is equal to 4.25 times 10 to the minus 4. Did I do that right?
I got 1.97 times 10 to the negative 3. Let me redo it.
That's x not times 3. Did you do silver concentration or x?
That was X.
No, you got silver concentration. So if I get my Ag plus, I get 1.27 times 10 to the minus 3.
No, that's what I got for X. Let me see.
Oh,
So
maybe I did something wrong. Did you remember the 27, the factor of 27 from the cube? Let me double check my work too. 2.6 times 10 to the minus 18 divided by 1.25 10 to the minus 11 power of Whoa, I got something different that time. Let me try this again. Oh. 18. Wait, what value did you get?
I got 1.97 times 10 to the negative 3.
I'm getting that now. I think I messed up my order of operations someplace. And if we multiply that, yeah, so I had a mistake on my calculator someplace, which is why I always appreciate the double check. 5.92 times 10, 5.92 times 10 minus 3. Hey, is that a good x small approximation? Yeah. Which is 10 to the minus 11. If x is bigger than the initial concentration, are we in a good place? No. No, this is terrible.
Because it has to be smaller, right?
It has to be smaller. It has to be at least, it has to be at least 1/10 for us to be good in this class. So this x is small approximation is horrible. Hey, this x is small approximation is definitely not working. Normally when I have this in a problem, and I'd have to look at the problem. Let me look at the problem real quick. Normally what I have is some note that's like, hey, use the x is small approximation and then tell me, is the x is small approximation valid or invalid? Let me see what I've got going on in this problem. But yeah, so this is a situation where the x is small approximation fails. I was suspicious about it because, and this is on 1.2, yeah?
Yeah.
Okay. Number 8.
For me, I plugged in the answer we got and it says it's correct with the x is small approximation.
Yeah, so I need to put a note in here that says go ahead and use the x is small approximation. What is the concentration of phosphate ions present in solution at the point where the second compound is? What's the concentration? What volume of 0.5 moles? Oh, this starts to ask some stoichiometry questions too. We haven't quite gotten to that in class yet. But yeah, so this is the let me add a note to this problem real quick. Yeah, so here the x small approximation is definitely failing. What do we do about that? Well, I'm sure we could go through the process of solving the entire fifth root equation and getting a real value for x rather than an approximate value for x, but I'll never ask you to do that. What I'll ask you to do in class is use the x small approximation and then explain to me whether it's good or bad and how you can tell. So for us, we look at this and we're like, okay, yeah, we can solve for x still using the approximation. We can tell really obviously is bad. Maybe not really obvious, but through some mathematical checks, we can tell it's bad. X is bigger than our initial concentration. X is definitely not small. So our answer here is kind of nonsense. This isn't a real answer. We'd have to go through and solve the fifth root equation to get the real value for x, which might be close to the same value. But right now we just don't know. This could be total nonsense. Okay, so I went ahead, I opened up an online equation solver, and I solved for the real value, non-approximate value of x, which is what we've got there in orange. It is still bigger than our initial phosphate concentration, right? And when we're not doing approximations, that's fine. Right? There's no approximation. That calculated value in orange, that is the exact value. Now, if you compare our x calculation to our, and I should say this is the calculated value of x. If you compare our approximate value of x to our actual value of x, clearly they're different than each other. Our approximation has overestimated our value by about a factor of 100, which would be 1,000% error. Really bad. But since that value in orange is no longer an approximation, it doesn't matter if it's bigger or smaller than the 10 to the minus 11, because it's not approximate. That's the real answer. So now we can continue the problem. Now this problem does some extra things here. Right? This problem does a little bit extra. We haven't done this in class yet, but now it's like, hey, what if you did some stoichiometry with this too? Right? In class today, we just got to the point where we started doing these calculations. We haven't started doing the stoichiometry. But this problem says, hey, if I give you some specific values, can you figure out the stoichiometry that's going on? It gives you a particular volume of solution. Oh, whoa, it gives you a particular volume of each solution. Did you dilute your concentrations before you did this, when you mixed the two things together?
Yeah.
Okay, cool. So we got to make sure we do our dilution correctly. I'm glad you did that, because like that would have thrown off our numbers a bit. But process is still correct. It's just our concentrations would have been a little off. So we can use these volumes and these concentrations to find the number of moles of silver ions before we add stuff and the number of moles of magnesium ions before we add stuff. Then we can figure out, okay, how much phosphate, if I have a particular concentration of phosphate, how much would I need to react all of my silver? So that's a 3-to-1 ratio. So doing the actual precipitation stoichiometry. And after we do that particular precipitation stoichiometry, how much of this X tells me I overestimated. So how do we go about this? Should we do this?
Yeah.
Even though we haven't done it in class yet? Okay.
If you guys are fine.
So I'm going to go ahead. I'm going to keep... I'm keeping so many things. Okay. I'm going to keep these calculated values here for X. I'm going to move them down a little bit. X is equal to 1.97 times 10 minus 3. And we're going to, now, on LabPal, it's going to ask us for the approximate value, but I'm going to keep track of the 6 times 10 minus 5, of the real value as well. So now that it's asking us how much, right, like particular volume we need, not concentration we need to reach, but particular volume we need, I have to think about the stoichiometry that's going to be happening. So I'm actually going to, I need like another color, not a different color. I usually only write things in red when I'm doing something that's wrong, but I just need another color so it like looks different. So now we need to do our stoichiometry. So this is number 8. Which part is this? This is like part F. Long question. Whew. Most of it's because I'm trying to get us to think about this step by step. You'll notice if you look at later problems, it's just like, give me the concentration of maximum separation. There's only one part, but you still have to do all of these steps to get that one part. It's pretty wild. So we're gonna go ahead. We're gonna look at the actual stoichiometry now. So, you know, there's this thing that we didn't talk about in class, which is, well, how much solid actually forms? We can actually ask that question now. Now, the silver, can you go ahead and give me your numbers for the volume and concentration of the silver before they're added together?
Yes. So there is 154 milliliters of 0.65 molar magnesium nitrate.
Oh, just the silver is the part that I want.
The silver? Okay, sorry.
Because we're not going to precipitate any of the magnesium anyway.
Okay. So 158 milliliters of 0.85 molar.
Okay. And then I'm going to have some volume of 0.5 molarity phosphate that I want to add to get it so both of these things completely react. So I'm going to go ahead and do this as a start, react, end, doing it as a stoichiometry problem. I'm going to go ahead and leave it in millimoles, which is going to drive you all crazy, but I love millimoles, and in a few weeks you will as well, I'm willing to bet. So this will be 130. Oh, actually I will convert this. This is going to be 0.1343 moles, and this is going to be 0.5 V moles. My react is going to be, if I have this set up correctly, If I'm doing like all of my silver is reacting, I'm going to go ahead and just say my silver is the limiting reactant, minus 0.1343, minus 0.1343, plus 0.1343 over on the product side.
What did you get 0.1343?
158 times 0.85 divided by 1,000. Unless I did that wrong. Right. Volume times molarity gets me my number of moles.
Yeah.
I was originally going to leave it in millimoles, but it turns out works out pretty nicely. Let me double check that real quick. 0.158 times 0.3. Oh, no, times 85. Yep, that's good. Okay. Now, coefficient on bottom of every mole ratio is 3, because that's the coefficient of the limiting reactant. Coefficient on top is which thing we're looking at. So for silver, it's 3. For phosphate, it's 1. For silver phosphate, it's 1. This thing goes to 0. This thing, 0.5V minus 0.1343 times 1/3. And 0 plus 1.343 and 1/3. Now, if I did this correctly, how much phosphate should be left over in solution? If I'm just doing the stoichiometry. Hopefully, this bit is also equal to 0. It's not actually equal to 0, right? It's going to be equal to 1.25 times 10 to the minus 11, approximately 0. We'll deal with fixing that bit in just a moment, but this is going to be approximately 0. The reason that's nice, if I'm doing this equal molar reaction, now I can solve for my volume, and I can figure out how much phosphate I would need to put in to react all of my silver. It's going to be 0.1343 divided by 3 divided by 0.5 times 1,000. .53 milliliters. That would react all of my silver and make me, I switched to decimal place off over here, sorry. That would react all of my silver, precipitate all of my silver so there's 0 left, and give me 0 phosphate concentration in solution. I don't really want 0 phosphate concentration. I want 1.25 times 10 to the minus 11 phosphate concentration. So I'd have to add just a little bit more. But here again, that 1.25 times 10 to the minus 11 is so small. It's 89.5. Like, honestly, again, this is where we're like, wow, this isn't practical. Because if I want to get to a concentration of 1.25 times 10 to the minus 11, I need like 11 sig figs of accuracy for my measurement. So I need glassware that's shockingly accurate. Now there are things called micropipettes. I don't think any of you have used those yet, but there are things called micropipettes where you can put in microliters of solution. Super, super accurate. So 10 to the minus 6 liters at a time. You can pick like 1 microliter, 2 microliters. You can put these you can do like 1/10 of a microliter. So it's actually not entirely impossible. But all of our glassware, everything we would do would have to be super accurate. You couldn't measure like 89 milliliters with a graduated cylinder and then go micropipette the rest in. Like, it just wouldn't be accurate enough. So in laboratory setting, really difficult to achieve. Computationally, pretty understandable. Now, here's the last part that's weird, which I don't even know how to fit on the board. The amount of silver that we have made is this number of moles. 0.1343 divided by 3. We have made, silver phosphate, not silver. I was distracted by our example earlier. Our moles of Ag3PO4 is equal to 4.47 times 10 to the minus 2. moles. Did I really make that much? Do I really have 0 silver left in solution? Is there ever 0 ions left in solution? No. So this 0 can't be right. Which means this number of moles I've made is more than nature actually made. Like, this is because we made approximations, we were running through calculations, we're like, pretend like the stoichiometry goes all the way, even though we know it doesn't. If the stoichiometry went all the way, that's how much silver we would make. There's this correction thing down here of how much silver ions left ended up back in solution, which is bigger than 0. Which means this number in red has to be bigger than it actually should be. So what we're going to do is I'm going to go ahead and label this from stoich. And I'm going to subtract off the moles from the equilibrium that are like, hey, that went back into solution. That didn't make solid. That went back into solution. I'm going to take this 1.97 times 10 to the minus 3. Okay, how am I going to do this? I'm going to do it for the value that LabPal accepted, even though the exasmall approximation didn't work. I'm going to take my that's still on the bottom of the screen. Okay, let's see here. Make sure you can see all of this stuff I'm doing. Okay, so I'm going to take this 1.97 times 10 to the minus 3. I'm going to multiply by 2 to get it to be my silver concentration. And then I have to multiply by my total volume. When you mix the two solutions together, it was 158 and 153 or something like that?
It was 312.
312? So I'm going to multiply by 0.312. That will get me the moles of silver ions left in solution. 1.97 times 10 to the minus 3 times 2 times 0.312. Oh, this is going to be a problem. Oh, it's not that big of a problem. It's significant, but it's not that big of a problem. 1.22 times 10 to the minus 3 moles. This is something we've never seen before in multiple ways. One, we haven't done this calculation in class yet, so we haven't even thought about this yet. We're getting a little bit ahead, which I always encourage. But this is the first time we've done a calculation where our stoichiometry from 127 is just wrong. Our stoichiometry from 120, if we just did the stoichiometry, this work in red, we would overestimate our amount of silver made. Let me get a number here. 0.22. Oh, that's not terrible. Let me check something. So that's the difference divided by that. Well, it's not nearly as bad as I thought. 4.47 compared to 1.22. This is about a 3% error, right? Our stoichiometry, so it's actually not even as bad as I thought. It's just all the calculations we've done in class. We haven't done this part of it before, but if we calculated like our error in stoichiometry, they've all been like 0.0000001% error. They've been like 10 to the minus 7, 10 to the minus 8 error. This is a 3% error in our stoichiometry. We are making less silver phosphate than we actually think we are because of that equilibrium phenomena. So not as bad as I thought, but still a significant amount. Like 4.47 minus times 10 to the minus 2 minus 1.22 times 10 to the minus 3. It's going to be a different number. It's going to be 4.35 instead of 4.47. It's not a huge difference. But our stoichiometry from 127 was a little bit wrong. And that's what happens when you start to get these things with really small concentrations or you know, equilibrium constants close to their concentrations. That was a lot.
Yeah.
That's a big problem. That, like I said, this is probably that one on this is 1.2. This is like one of the hardest problems I could give to you, not just for this material, but like this quarter.
Okay.
Just to put it into context of like how hard this is. Now, some people, when we start doing our acid bases and our buffers, they'll be like, no, this is way harder. I think this is harder. Very closely related to our acid bases and our buffers, but I think this is probably in my opinion, is probably in top 10 hardest problems of the quarter. Just so if you're freaking out and you're like, I can't understand what's going on, it's like, this is putting together like 5 different things. We've got our equilibrium of 2 different things together. So we've got competing equilibrium, we've got stoichiometry, we've got excess small approximation failing, like we've got the redissolve being significant, you know, this idea of overestimating our stoichiometry being a pretty big percentage. Like there's a lot going on in this problem. But hopefully that walkthrough helps.
Yeah, that was really
A lot of different concepts to talk about.
I have a quick question. Like,
Sure.
I get the equilibrium part,
Mhm.
like how to do it, but when I'm trying to get X, I get a different thing on my calculator.
Let me see what's going on here. Is this the proper way to do powered roots?
Because I barely got it, so I'm not like not
This
so
calculator- Okay, I find these calculators too complicated.
Okay.
Okay, so let me think about something real quick. Let me show you the way I do
Okay.
roots on my simple calculator that I like.
Thank you.
See ya. So here's the way that I do roots in my simple calculator. And I like it better. Like I like my simple calculator.
Yeah.
Those big calculators, like they always confuse me.
Mm-hmm.
But like they're nice because the way they let you track things, and we can figure out the right way to do it. But the thing that I do, let's say we've got 400 and we want to take the square root. That would be equivalent to 400 to the power of 1/2, which is equivalent to 400 to the power of 0.5. So I just do 400 to the power of 0.5. Same thing if I wanted to do the cube root, right? If I wanted to do the cube root of 400.
Then it would be 1/5, right?
Cube root?
Oh no, wait, sorry. Over
1/3.
the third, yeah.
Which would then be 400 to the power of 0.33333.
Okay.
And if so, you've got 4th root that you're trying to do.
Yeah.
That'd be like 400 to the 4th root would be 400
over 1/4.
to the 1/4.
Yeah.
Which would be like 400 to the power of 0.25.
Okay. Oh my God, thank you.
And that just makes my life, like for me, using these simple little calculators.
Yeah.
Like I know there's like a root. Yeah, so I've got a x root y button, but I always mess it up.
No, yeah.
I always mess it up. So I just do it this way. It just works better for me.
No, thank you. Okay.
Now let's see. Back to recording. We're going on to our next problem. Like I mentioned, number 8 is kind of one of the hardest problems. In my opinion, one of the hardest problems of the quarter. Kind of nice that we see those hard problems early. Little daunting if you weren't ready to see one of the hardest problems of the quarter already. Like, sorry. But that is, the good news is, like, if you can wrap your head around that, not just the math, but chemically what's happening, you're probably in pretty good shape for tackling a lot of things this quarter. We're now going to switch over to number 7. So this is 129, MQ 1.2, number 7. I'm also going to change my blue ink because this pen is dying. So the problem says silver nitrate slowly added to a solution that's got some concentration of chloride ions and some concentration of bromine ions. It gives us the KSP, assuming the x, a small approximation, is valid for this calculation, find what will precipitate first, what percentage of the first anion that precipitates will be left in solution when the second compound starts to precipitate. So this is a full competitive precipitation problem, like the entire problem we did today in class that took us 20 minutes to do, 25 minutes to do. That's just like one box is the answer. So let's go ahead and set up our thinking for this. And this one is extra weird because it's doing it for anions instead of cations.
Yeah.
Most examples we see are adding an anion to separate cations. This is doing the flip of that, but all of the logic is actually still the same. Here I'm going to be increasing my Ag plus concentration. The nice thing is they're all 1-to-1 ratios. I need my KSP for silver bromide is given. That's a KSP of 5.0 times 10 to the minus 13. And we've also got our silver chloride, which has a KSP of
1.8 times 10 to the negative 10.
Nice thing here is since they are two ions, one cation, one anion, I can just directly compare the KSPs, nothing like that weird thing that happened in problem 8, I think, before you were here.
Yeah.
We had something weird happen in problem 8. In this situation, I can just compare. I can say, look, AgBr has the smaller KSP. AgBr is going to precipitate first. And technically, this is not the precipitation. This is where it saturates. And then up here, this is going to be where AgCl saturates. Now, it's not asking anything about this first point. It's just asking about the second point. And this is where concentration of Br minus should be approximately 0, but it's not actually 0. So I'm just going to go ahead and I'm going to skip doing that first. So we just have to do 2 equilibrium tables. I'm going to skip the one for, there's nothing in the problem asking about like the silver ions to saturate bromide. I'm going to skip that one. I'm just going to do silver ions to saturate chloride and then how much bromide is actually left. So I'm going to go ahead, I'm going to set up AgCl goes to Ag plus Cl minus. My chloride concentration, the random value it gave me was 2.1 times 10 to the minus 3, or gave you 2.1 times 10 to the minus 3. We're saying 0, we're figuring out how much we need to add in. This is solid, this is aqueous. Sorry, I forgot my states of matter. Don't forget your states of matter. That's all that. This is plus x, x, 2.1 times 10 to the minus 3 plus of x. I'm going to go ahead and just approximate. I'm going to have 1.8 times 10 to the minus 10 is equal to x times 2.1 times 10 to the minus 3. I can solve for x pretty easily just by doing a division. Did you do this part already?
Yeah, I got.
What'd you get?
I got 8.57 times 10 to the negative 8.
Great. That's a molarity. That's going to be my silver concentration. That's going to be my silver chloride that redissolves. That's a small approximation is good, right? Even though 2.1 times 10 to the minus 3 is pretty small, my KSP is way smaller, and the x value I eventually calculate is way, way smaller, right? It's like 10,000 times smaller than my initial concentration. Now, what the question is really, we needed to do that work so we can answer the real part of the question. The question says, how much bromide ion is actually left in solution? Like, how good is our percent separation? At the theoretical limit, my silver chloride, my chloride ions are all left in solution. Full concentration, the 2.1 times 10 to the minus 3, all of that's still there. The bromide concentration is 0. So it'd be like 0% left in solution. Because it'd be 0 divided by the initial concentration. not really 0. So now we have to go ahead and do this calculation. This is where the x small approximation might get into some trouble. We got to do AG BR, solid, goes to AG plus aqueous plus BR minus aqueous, where my bromine is approximately 0, and my silver is 8.57 times 10 to the minus 8. Oh, I think x small is going to fail again, because I got minus 8 minus 13. This is going to be cutting it close. Minus 8 minus 13. This is about as much as I think I want to handle. We'll see what happens. Plus x, 8.57 times 10 to the minus 8 plus x and x. Oh, this problem says to assume x is small is valid. Or it says to use x is small. So we're going to use x is small. I think it's not going to work. I think this is going to be a bad x is small. Let's see though. So I'm going to have 5.0 times 10 to the minus 13 is approximately equal to 8.57 times 10 to the minus. Oh yeah, that's gonna not work. I'm gonna solve for my x. I can tell the x small approximation is not going to work because I can just do the math in my head a little bit, but let's figure out how bad it is. 5.0 times 10 to the minus 13 divided by 8.57 10 to the minus 8. Yeah. So I get an x value of 5.83, and I didn't give myself a little space there. 5.83 times 10 to the minus 6.
What do you want it to be at?
Well, I want x to be at least a factor of 10 smaller than the initial concentration. Here I've got my x bigger than my initial concentration. So x is bigger than what I started with, which means the x is small approximation did not work. So, whoops. X is small approximation is not valid in this situation. The problem says to go ahead and use it. I might add a note on there that's like, hey, talk to a friend. I think I actually do.
Yeah.
You got to go talk to somebody about like, why is it valid, why isn't it valid, what we do. You just solve the quadratic to get the real value. We can do that in a minute. I usually am curious when the x is small approximation fails. I'm like, well, how off am I? So almost every time I see one of these, I'm like, I'm going to go solve the quadratic and actually figure out what's going on. I don't solve it by hand. I use an online equation solver, but I solve it because I'm curious. Just want to know. So back to the actual question, though. 5.83 times 10 to the minus 6. Not 0, but pretty small. So I'm going to take that 5.83 times 10 to the minus 6. I'm going to divide by, to get my percent of ion left in solution, what I'm going to do is I'm going to do x divided by my BR minus concentration initial times 100. And that's going to be percent left. So I think this is going to be a really small percentage. So I'm going to go ahead and do the 5.83 times 10 to the minus 6 divided by the initial concentration you were given, which was 2.1 times 10 to the minus 3, 2.1 times 10 to the minus 3. And I get 2.77 times 10 to the minus 3. Which is going to be like times 100. I forgot to times by 100. So that's going to be like 0.277%. Is it about this one? No, something else. Okay.
Wait, sorry, what did you divide it by again?
The original concentration of the bromide ions that was given in the particular problem. That is it? Do you like Alexander or Alex?
Alex is fine.
Alex, that Alex had. So I looked up Alex's
Okay.
specific numbers. You might have slightly different numbers.
Yeah.
Or completely different numbers. I'm going to pause the recording for a moment so I can input this online. Okay, so I went ahead, I plugged in the full quadratic into an online solver. Because I was just curious, right? You don't need to do this for the homework, right? But that is one of the things I mentioned earlier, I'm going to mention again. There's a difference between doing the homework and using the homework. Right? Doing the homework is you get all your green boxes and you're like, fine. Come on in. Using the homework is this kind of thing where you're like, hey, what's actually going on here? How can I make sense of this? Not just this individual problem, but like the theme of all of the problems together. Am I kind of doing this like beyond thinking of like, okay, I see how this problem is set up and how this problem is set up and how they all kind of like lead to each other. So there's nothing that tells you need to solve for the exact value of x by not using the approximation, but you should be curious, you should be interested, you should find out. So I calculate 6.65 times 10 to the minus 7. That's a pretty big error. That's like, you know, more than double. So we're looking at like 100% error. Oops. Okay, so the x is small approximation. Now the problem tells us to use the x is small approximation. But the x is small approximation is not that great. Our x is more than double the size. That's more than 100% error. So not great. But in the grand scheme of things, 5.8 times 10 to the minus 6 versus 6.6 times 10 to the minus 7, our percent error in the overall estimation of like how much bromide ion is left in solution, I think it's like 0.2% error versus 0.02% error. Definitely something to be aware of and to think about and to kind of notice. These problems where we're doing, you'll notice if you look at the first few, like 4, 5, 6, I don't even know if those are these competing solubility problems. But there's a lot of cases where the x is small approximation is completely valid. The thing that becomes problematic later in the quarter, but more importantly later in life, especially again for those that are going to the medical field, there's all kinds of situations where the x is small approximation is being used in non-obvious ways and causes all kinds of issues. And if you're not aware of it, like, it causes problems. It's just like, you're like, this thing isn't working, my buffer's not working, my cell cultures keep dying, my medicines keep going bad, like all these things. And it's like, oh, because the x is small approximation isn't valid in this situation. But the Henderson-Hasselbalch equation that a lot of people use in the medical field and these other places, we're going to learn about this quarter, Henderson-Hasselbalch approximation, or a Henderson-Hasselbalch equation, uses the x is small approximation twice in it. That's not obvious anywhere. And so sometimes there are people who come and take Chem 129. They've taken bio classes where they've used the Henderson-Hasselbalch equation, and they've never known like how it works. They're just like, oh, I just plug the numbers in and I get a value out. It's like, yeah, but there's approximations built into it. And that's part of why you get different allowed pH ranges for your buffers, is because you're allowed to have different percent errors in your x is small approximation. So some people, most people are pH, oh, okay, I'm getting way ahead. We'll deal with that when we get to buffers. But there's a place where the x is small approximation is just happening that people don't know about if they take this, if they learn about buffers in a different class. So that was number 7 for you. Did you have a question on number 7 as well? Because you looked excited when you saw this on the board.
Yeah, I solved it, but I just wanted to have a verbal explanation of that as well.
Okay. So I'll go through the verbal explanation again, and then we'll do number 6.
I might have cut it too close, but I can
Oh,
watch
because
the
you're
video.
going again. You have to leave in like a little bit.
I have to be at tutoring at 2.
Okay.
So I don't want to interrupt your thing, and I can watch the video. So if you go over 6 after this, I would love it. I'd watch it.
Okay.
Yeah.
I'll go after 6 after this. Let me see where you're stuck though. Hang on.
Well, no, I.
So let's go ahead and talk through number 7 again. Number 7 has a weird setup. The example we did in class today, most of the examples you see on the homework, they're separating cations with a particular anion. Here, we're separating anions with a particular cation. The first thing we have to do is we have to figure out which thing is going to saturate first, which thing is going to precipitate first. The nice part is, since it's all 1-to-1 ratios, it's just the smaller KSP precipitates first. So I know that silver bromide is going to precipitate first, which means I'm going to hit its saturation point first, and then it'll start to precipitate. Then, if I keep adding silver ions after that, eventually I'll get to this point where the bromide is completely knocked out, approximately 0, and that's the saturation point for the silver chloride, where the silver chloride would saturate and then start to precipitate. Now, there's nothing in the problem that actually asks us about the first point, the silver bromide saturation. So I'm skipping that ice table and I just go straight to calculating what's the concentration of silver ions to get to that second saturation point, this spot up here where the silver chloride will saturate. So I go ahead and I just set up an equilibrium table with some initial chloride concentration because there was chloride in solution already. I solve for my x value, and my x value, my silver concentration, ends up being this really small value of 8.57 times 10 to the minus 8 molarity. Really small value. Doesn't get into the stoichiometry beforehand. That's number 8. We can talk about that later if we'd like. But that's the point where we've hit that saturation. And then we say, okay, at that concentration of silver ions, bromide ions are approximately 0. But what are they really? They're not actually 0. So I set up a second equilibrium table to fix that approximate 0. So I have my silver concentration at that point. I've got my bromide concentration approximately 0. And I just set up my equilibrium table. I solve. I get x equals 5.83 times 10 to the minus 6. And we go, oh no, x's small approximation is not valid here. Right? My x value is bigger than my initial concentration. The only way that x is small works is if x is significantly smaller than the initial concentration. Here the initial concentration is 8.57 times 10 to the minus 8. My x is bigger than that. No good. The problem tells us just use the x small approximation anyway. Go talk to somebody in the class about whether that's valid or invalid. Because writing additional things for you, because I don't want you to solve the quadratic, I want you to understand like the idea of the approximation. Turns out it's not valid. We should solve the quadratic. If we solve the quadratic, we get an exact value. That's the value in orange. We've got about 100% error when we use the x small approximation, because the x value that we predict with the x small approximation is about 10 times bigger than the actual value, than the exact value. So we've got pretty big error there. But, you know, the problem says, go ahead and use the x small approximation. What's the percent of bromide ions left in solution? So I take the amount that I had calculated of bromide ions left in solution, I divide by the initial, multiply by 100, that gives me the percent left. And it's like 0.2% left, 0.3% left. Yeah, small percentage left. So what that means is we did a really good job creating separation. All of our silver ions are left in, like 100% silver left in solution, 0.2% bromide left, sorry, not silver, 100% chloride left in solution, 0.2% bromide left in solution. Rather than 100%, that bromide is down to 0.2%. Good separation. And if we actually used the exact answer, it's even better than 0.2%. It's like 0.02%. So that's a situation where we've got pretty good separation of our ions. And again, this is all just like a new control mechanism, where now we could do this with, instead of silver, we could do this with lead, and we might flip which one separates and how well they separate. But we've got different ways that we can go about doing separation. We can leave something in solution, knock something else out of solution. Precious metal mining, silver mining, gold mining, were often done with this selective precipitation, where you could force the silver ions, like if you had like a vein of silver in the wall, but it was like not thick enough that you could mine it, you could just take all of the rock slurry, you could wash it with something that would push silver ions into solution, take all of the water that's got your silver ions in it now, and then reprecipitate the silver ions back out. So old school like mining was done this way. Some modern mining is still done that way. If you can't find like good deposits, but you're like, oh, we know the soil has it, you can do that. Yeah. I was asked to do number 6. Oh. We've got 10 minutes left in office hours. I was like, wait, I've got class at 2 o'clock. Do I have time to do number 6?
I have a question. What is this? What are you guys doing right now?
This is from Chem 129.
Yeah.
Master question 1.2, number 7. We did number 8 on earlier in office hours, and I did record it, and I'll post that in a little while. I've got class for a while. Sometime tonight I'll post it. It's going to be a long day for me.
I think I can ask a quick pre-lab question.
Sure. Yeah.
It's like a conceptual one in a way. It's the dissolution of. It just says dissolution from a precipitation reaction upon the addition of acetic acid. So my precipitation is.
I think you've got one thing wrong, and that's so you've got 2 things wrong. So the first is the calcium acetate here. That's going to disassociate into ions.
Okay, since it's aqueous.
Because it wants the net ionic.
Oh yeah.
So that's aqueous. Break it apart, and you should be okay.
Okay. So that's it?
I think that's it. I think if
yeah,
you break it apart, you'll be okay.
Everyone was like struggling with that, but
yeah,
probably just
I think
that.
it's just disassociate it, and you'll be okay.
Okay, thank you.
I don't have time to do number 6. I'm gonna start it. Let's start number 6 real quick. And then I gotta go to office hours. I mean, office hours. I gotta go to class. I got another class.
That was a long day.
I got class from 2 to 3, and then I've got an hour break, and then I've got class from 4 to 6. That hour break is my lunch time. And sending emails to people. I meant to send an email this morning to one of my other classes, and I just didn't. Okay, so number 6. If we read number 6, I'm going to go ahead. I've still got Alex's numbers open, so I'm just going to do Alex's number 6. Which got it right. Selective precipitation. A solution has lead ions and silver ions. If selective precipitation is to be achieved with sodium chloride, what's the minimum concentration to precipitate the compound that precipitates first? So what we've got going on here is we are adding chloride ions. We've got lead 2+. We've got silver plus. That silver plus is going to become AgCl, which has a KSP value. I've just used this one so much today, I have it memorized. Times 10 to the minus 10. And lead, which is going to go to PbCl2, is going to have a KSP I have to look up real quick. I've got it right here. 1.7 times 10 to the minus 5. So based on this, I would look at this and I'd say, okay, the smaller KSP value is the thing that's going to precipitate first. So I think AgCl is going to saturate first because it's got the smaller KSP value. The lead chloride is going to saturate second. So that's that saturation point. That's that saturation point. That's the important first thing. So then the question is asking us a couple things. It's A, Cl minus to saturate, Ag plus. Right, and the thing is, once we start to reword it, this starts to seem obvious. This is just what we did in class. The part that makes these problems difficult, and this is intentional, unintentional on my part, right? Every person you talk to kind of approaches problems in a slightly different way. They word things slightly differently. And one of the main things we have to work on in chemistry, not just chemistry, but in all things in life really, is how do I develop a common language with the person I'm talking to? How do I get through their perspective and their way of thinking about it to what's really going on? Sometimes this is emotional space, we do this. Sometimes this is historical context. Here it's chemistry context, right? How do we get through all this language to really just be like, what's really going on, right? So calculation A, we did that in class. Calculation B then becomes no calculation at all. It is, right, once we understand lead is still there, it's the Pb2 plus concentration it's asking what's the lead concentration in solution before the second compound begins to precipitate. It should be the same as it was. Right, the lead concentration, since lead is the second thing to precipitate, the lead concentration should be the same. Right? As long as I'm getting just to this point, I'm not going past it, lead concentration is not changing. So my lead concentration is just the value that's given in the problem. Part C is asking for Cl minus to saturate Pb2 plus. Okay, so that's asking for the concentration. That's asking to saturate the lead 2 plus, which is just an equilibrium table with that. And then part D is, you know, at this point, we've got that Ag plus concentration approximately 0. And that's asking, part D is asking, what's really your silver concentration at that point? It's not 0. Hopefully it's close to 0, but what's the real value?
So it's like, part D is like number 7.
Yeah,
Okay.
part D is like number 7.
Alright. So it's just kind of, you're going in order of, like, the lines. Just first
Yeah.
saturate.
And that's the way I usually think about these to start. But then when we start getting good at these, we're like, you know what, just do D.
Mm-hmm.
Right?
Mm-hmm.
All of this stuff is to set up how we think about it, but D is the only place where something interesting is going on.
Mm-hmm.
So we get to this point where it's like, yeah, no, just do the interesting part. Okay. I'm gonna stop this.